In this video, we will cover an introduction to OpenFlow. We'll focus on how packets move through an OpenFlow network. We will see packets in flight using Mininet network emulation and Wireshark. Also, we will do a packet walkthrough of an HTTP request and reply through the OpenFlow network. Finally, we will look at the Open Networking Foundation specs for what makes an OpenFlow switch. So briefly, before we jump right in, what is OpenFlow? The OpenFlow protocol is a standardized protocol for interacting with the forwarding behaviors of switches from multiple vendors. This provides us a way to control the behavior of switches throughout our network dynamically and programmatically. OpenFlow is a key protocol in many SDN solutions. Much more detail on OpenFlow and SDN can be found at www.opennetworking.org. So let's jump right in. The network I'm going to launch will look like this. We will have an OpenFlow kernel switch S1, the OpenFlow reference controller C0, and 4 emulated hosts H1 through H4. I'll launch a simple web server at H4 and do an HTTP request from H1. Then we will look at a packet walkthrough of what happens in this OpenFlow-enabled network, as well as look at the captured packets in Wireshark. I'm using Mininet to emulate this network. If you are not familiar with Mininet, I'd suggest going to mininet.org for more detail, or watching my Introduction to Mininet video on my YouTube channel. So I'll run sudo mn --topo equals single, comma 4. So I've launched my topology. The Mininet dump command shows my nodes. Since I'm not specifying a controller, Mininet will run the OpenFlow reference controller, which will be C0. I'm also running Wireshark as a background process, and I'm capturing on my loopback 0 interface from my Mininet VM. In Mininet, communications to a local controller happen over loopback 0. I'm filtering in Wireshark for OpenFlow packets with OF. On host H4, I'm going to launch a simple Python web server. So H4 python-m simple HTTP server on port 80, and I'll run that as a background process. Now let's do a wget command from H1. So I'm doing an HTTP request from H1 to the simple web server on H4. So I'll do H1 wget 10.0.0.4, and we see that works. And switching to Wireshark, let's pause this capture. And we see we got some nice OpenFlow packets. We'll come back to these packets later in the video. First we will look at what just happened via diagram. Here is the diagram we were just looking at. Let's look at what happened when I made my HTTP web request from H1 to the simple web server at H4 a moment ago. We are going to skip ARP and focus on the HTTP request. So host H1 did an HTTP GET to H4. Since this is TCP, TCP conversations always start with a SYN message. So here's the SYN packet. If this was a traditional switch, the packet would be forwarded onto H4 based on knowing where H4's MAC address is. However, since this is an OpenFlow switch, S1 will check its local flow tables. Since this is the first packet of a flow, it probably doesn't have a flow entry matching this packet. This is called a table miss. Usually when there are no matching flows, the default action is to punt this packet up to the controller. Packet in. So S1 will send a packet in message to the controller. This packet in message encapsulates the original TCP SYN message inside of it. It might include the entire packet, or it might include just some of the packet headers and reference a buffer ID. When using a buffer ID, the switch buffers the entire packet, and the controller can later instruct the switch what to do with the stored packet by referencing the buffer ID. So the controller gets this packet in message. Typically a couple of things can happen here. The controller might send a packet out message and or a flow modification message back to the switch. Packet out. A packet out message is an instruction from the controller to the switch about what to do with a specific packet. The packet out message might contain a complete encapsulated packet, or it might reference a buffer ID of a packet the switch is storing. So in this example, the controller instructs the switch S1 to simply send the packet referenced by buffer ID 250, this was the TCP SYN message, from H1 out its port 4 towards H4. Flow modification. Alternatively, the controller might also send a flow modification message. A flow modification message instructs the switch to install a new flow entry in its flow tables. Flow entries let the switch know what to do when future similar packets arrive at the switch based on matching fields and masks. So in this example, a controller might send a flow modification message saying effectively, Any TCP port 80 requests from the IP and MAC of H1 to the IP and MAC of H4, send all of those out your port 4. A flow modification message might also reference a buffer ID. This would tell the switch that first packet you buffered, number 250, release that packet from your buffer and apply the actions in this message to it as well. This example is a simple single action, but many sets of actions are possible. For example, actions can include changing multiple headers, like IPs, MACs, and TCP ports. We could pop, push, or swap MPLS labels. We can also take actions like flooding out all ports, dropping the packet, or telling the switch to send matching packets to the controller. We can even tell the switch to use its normal non-OpenFlow packet processing. Timeouts. We can see in the flow modification message two kinds of timeouts. The timeouts tell the switch how long to cache a flow entry. So in this example, we have an idle timeout of 20 and a hard timeout of 60. The idle timeout of 20 means if there are no matching HTTP requests for 20 seconds, remove this flow entry. The hard timeout of 60 means after 60 seconds, no matter if there are live matching packets or not, no matter what, remove this flow entry. Priority. The priority is very important as flow entries are sorted by their priorities. So if two flow entries match a packet in the same flow table, the one with the higher priority will be used and the other one will be ignored. So this flow modification message results in a new flow entry on the switch S1, and since it referenced a buffer ID, it also results in the original TCP SYN message packet getting forwarded out port 4, just like the action says to do. So this same process will happen in H4's reply to H1. So here's a good chance to review up to this point. H4 replies to the TCP SYN with a SYN ACK. The SYN ACK arrives at the switch. The switch S1 has no specific flow entry matching this packet in any of its flow tables. It still has a flow entry for the SYN packet from H1 to H4, but not for this SYN ACK reply. Again, this is a table miss, and a table miss flow entry will normally instruct the switch to send this packet to the controller. So S1 encapsulates the reply into a packet in message and sends it to the controller. This might be the entire packet inside an OpenFlow packet in message, or it might be just some headers from the packet along with the buffer ID reference number, in this case 251. The SDN controller then typically sends a packet out and/or packet modification message. The packet out message tells the switch what to do with a specific packet. Again, the controller might send the entire packet it wants sent encapsulated inside a packet out message, or it might reference a buffer ID stored in the switch saying, your stored packet at buffer ID 251, release that with the following actions. The controller might also send a flow modification message telling the switch what to do with future packets matching specified fields. The flow mod message may also have a buffer ID to reference a currently buffered packet on the switch. It also has the timeouts, the actions to take, and the priority as discussed before. So after all of this, if there were flow modification messages to the switch, the end result is simply some flow entries cached on the switch S1. This means that the rest of the conversation between H1 and H4 won't have to go up to the controller because the switch has flow entries in its flow tables telling it what to do with the packet. So you would see the completion of the TCP handshake go through, as well as the HTTP request and HTTP reply go through the switch S1 without any need to talk to the controller C0. One final note on this diagram. In this example, we're looking at OpenFlow being reactive. Flows are established on the switch in response to seeing live packets. OpenFlow applications can be proactive instead and pre-install flow entries on switches. In this way, the switch would not have to contact the controller if flows are pre-established on the switch before a matching packet is ever seen. So let's see all this in our Wireshark capture. Again, we will skip ARP for the purposes of this review. So here is the packet in message from the switch to the controller. We see here the switch is using a buffer ID to reference this packet. And we see some fields from the original packet, source and destination MAC, source and destination IP, and we also see the source TCP port and the destination TCP port of 80 for HTTP traffic. Flow modification. Here we see the controller has sent a flow modification message in response. We see some of the match fields and types. This particular flow modification is very specific, calling out source and destination MAC, source and destination IP, and even source and destination TCP port. The presence of source TCP port as a match means this particular flow modification message will only match this particular HTTP session, and not say the very next new session that H1 starts with the new TCP source port. That just happens to be the behavior of the reference controller I'm using in this demo. Other controllers, of course, may have different behaviors. We can see the timeout set. So here we have an idle timeout of 60 seconds and a hard timeout set to 0. This 0 setting just means the hard timeout is not going to be used. Here we say the minimum priority of 0 is set, and here is a buffer ID. So this field being here, this is telling the switch you had a packet with buffer ID 282. That packet you should take the following actions on. And here we can see the action set. In this case, there is only a single action, which is send this packet out port 4, which is the port connected to host H4, the web server. There can be more than one action, though, which is why this is called an action set. So this packet in message and this flow modification message were a result from the TCP SYN message sent from H1. And in response to the SYN message from H1, H4 sent a SYN ACK message back. That SYN ACK message got encapsulated by the switch into a packet in message for the controller, and the controller replied with another flow modification message for the return flow from H4 back to H1. After that specific example, let's step back and look at some details about what makes an OpenFlow switch. The Open Networking Foundation, or ONF, defines that an OpenFlow switch contains one or more flow tables, each of which are meant to hold flow entries. An OpenFlow switch also has a group table with group entries, which contain action buckets. Additionally, there is an OpenFlow channel for the connection to one or more controllers. Flow tables. There has to be at least one flow table for an OpenFlow switch, but there can be more. Each flow table is there to hold flow entries, as we have discussed before. Flow entries. Flow entries have match fields to match against incoming packets to the switch. Flow entries also have instructions for what to do with matching packets. For example, an instruction could be to add an action to a packet, like send out port 4, or maybe to change the source and destination MAC address. An instruction can also be to go to a later flow table where another match and more instructions can be. Flow entries also have priorities, as discussed earlier. So if a packet matches multiple flow entries, only the highest priority entry will be used. So in this example, where we have 3 flow entries in this flow table 1, the first one has a priority of 100, the second 50, and the third 0. If a packet matched all 3, only the priority 100 flow entry would be used. If you are familiar with access control lists or ACLs and routers, I'd like to think of a flow table as an ACL on steroids. It's like a super ACL that's dynamic, programmable, and with a lot more ways to match packets and a lot more actions to take than the typical permit and deny in an ACL. Group table. The group table is like a special kind of flow table. The group table consists of group entries, which include an identifier and an action bucket. An action bucket is really what makes the group entries unique from regular flow entries. The action bucket lets you do some things like send copies of the same packet out multiple ports. Like in this example, we might have an action bucket that says to send a packet out ports 2, 4, 5, and 10. Compared to the complexities of multicast today, this is a very nice feature. Action buckets can do other tasks, such as have multiple actions, and have the switch pick from one amongst them. For example, with ECMP, or load balancing traffic, the switch can pick one from a set of next-up IPs or output ports. Another advantage of group tables is the ability to map multiple flow entries to the same group entry. So you could have 100 flow entries that all point to, say, group entry 30, which says send packets out port 2. If you change this group entry to send packets out, say, port 5 instead, you're effectively changing the behavior of the 100 flow entries pointing to this group entry in one swoop. OpenFlow channel. Finally, we have the OpenFlow channel. The channel is for communication between the switch and controller and where the OpenFlow protocol messages will traverse. This includes the packet in, packet out, and flow modification messages we talked about earlier. It also includes items like communication setup between the switch and controller, periodic health checking echo messages, status information exchange, flow removal requests, and other OpenFlow protocol messages. Communication over the channel can be TCP, or for encrypted communication, it can use TLS. One last item I want to mention here is counters. OpenFlow tracks a lot of counters on the switch, including counters for every flow table, flow entry, every port, queue, group table, group bucket, and for QoS meter and meter band. I didn't cover meter and meter bands in this video, but more information can be found from opennetworking.org. And that's it. I hope you found this video useful and starting to learn about OpenFlow. You can reach me via LinkedIn at linkedin.com/in/David Mahler.